Thank you for the kind introduction, and thank you to the conference organizers for such a fantastic conference. It's truly a pleasure and a privilege to be here. Good morning, ladies and gentlemen. Let's talk about quantum error correction. Quantum error correction is clearly absolutely fundamental to the future of quantum computing, and is also a key part of IBM's roadmap towards achieving scalable fault-tolerant architectures. And it's a particularly exciting time for quantum error correction because, as demonstrated so wonderfully by the first plenary speaker, we're in a position where we can actually build small quantum error correction codes in real hardware and see how well they work. Isn't that wonderful? It's incredibly exciting. It leads to the question of how might we scale such an architecture to something much larger, something that is capable of running large and interesting quantum algorithms. Now, the big question here is what quantum error correction codes are the most suitable for large fault-tolerant architectures? If you were to look through the literature today and look for what quantum architectures are the most mature, you would probably immediately find surface code quantum computers. Surface codes are amazing in many ways. They have a very high noise threshold. They are implementable on a nearest neighbor lattice, so that makes them particularly readily realizable in certain hardware architectures. And finally, it's also quite well known how to do logical operations in a surface code quantum computer. There's a lot of work benchmarking various practical quantum algorithms in surface code architectures. However, surface codes also have a significant disadvantage, and that's that they have a relatively poor encoding rate. So that means if you want lots of logical qubits, you're going to need an absolutely astronomical amount of physical qubits in order to accomplish that. So some proposals estimate the amount of physical qubits required for interesting quantum computations to be on the order of millions or tens of millions. And that's a significant obstacle to making quantum computing practical. Part of the reason for this is an interesting limitation that surface codes have. And that's if you are investing new physical qubits into a quantum architecture, you sort of have to decide, am I investing those physical qubits into more protection? So am I making my surface code patches larger, thereby being able to protect against less and less likely errors? Or am I instead adding more and more surface code patches, therefore allowing me to have more logical qubits? It's sort of one or the other, either more protection or more logical qubits. And what's very interesting is that there's been a lot of progress in quantum error correction recently on families of so-called low-density parity check codes, abbreviated LDPC codes, that don't have this restriction. When you scale the number of physical qubits, you scale both the amount of protection that you get and the amount of logical information that you store. So this is a really fantastic property, and we would really like to be able to leverage this in a quantum architecture. So this takes us to our primary research question for this work. Can we find an example of a small quantum low-density parity check code that outperforms surface codes? So what do we mean by outperform here? The main deliverable was a higher encoding rate. We want more logical qubits per physical qubit. And second, we want this to be an actually feasible demonstration someday. We want to build this in hardware. So whatever the requirements of this LDPC code are, it needs to fit into the capabilities of an existing hardware architecture. At IBM, of course, we're particularly interested in superconducting quantum computers. So this is maybe a cartoon of what a superconducting chip might look like. You have a bunch of qubits that are connected by nearest neighbor wires, and this is something that's clearly very suitable for a surface code architecture. Can you do better using a chip that looks like this? Well, there is actually a result by Braviterel and Poulin back from 2009 that shows that if you have an architecture that looks like this, where all the qubits are connected by nearest neighbors, then there's actually an upper bound on how well any quantum error correction code could do. And furthermore, surface codes saturate that bound. So if you're hoping to do better than surface codes, then you're going to need additional hardware capabilities than this. For the purposes of this talk, we were interested in two additional capabilities. First, we were interested in what you can do with long-range connections. So now you can have very distant qubits talk to one another on a superconducting chip. At IBM, we call this a C-coupler. And then the second capability is that we consider two chips on top of each other, so a bilayer architecture. On any particular layer, you're limited by the fact that your wires cannot cross. You're limited to planar connectivity graphs. But in an architecture like this, you could imagine two planar graphs, each one of which can couple to the same physical qubits from either the top or the bottom. So notably, this doesn't give you access to any connectivity graph. It still requires that your graph is sort of almost planar. It can be decomposed into two planar graphs, but it does vastly widen the number of the possibilities. It gives you access to much more complicated connectivity graphs using these capabilities. So having set the stage, let's take a look at the family of quantum error correction codes that we propose in this work. We call them bivariate bicycle codes. This name is derived by the algebra that is used to generate the definition of the code. However, for the purposes of this talk, I thought it might be more interesting to give an entirely visual characterization of this talk. This is actually by no means a simplification. This is just a fair way of defining these codes. And it starts in hopefully a familiar place. It starts with toric codes. So let's remind ourselves briefly what toric codes look like. They start with a lattice on the torus, and we're going to place physical qubits on a checkerboard pattern. Here I'm showing them on only one region of the torus. And the remaining cells of this torus are going to be our check vertices. So we have a set of X checks and Z checks. If you're not familiar with this graph notation for error correction codes, the basic idea is that if you have a Z check here that's connected to 4 neighboring physical qubits, that means that we want the poly ZZZZ on those 4 qubits to be as part of the stabilizer. So this quantum error correction code has equally many checks as it has qubits. However, it turns out that 2 of these checks are redundant. So as a consequence, we have a quantum error correction code with 2 logical qubits. You can make this quantum error correction code give you more defense against errors by making the torus bigger. You can make the dimensions of the torus larger. However, as you scale up, you don't get more logical qubits. That number remains fixed. So it's like the surface code in that way. So how do we go from toric codes to bivariate bicycle codes? Well, it's quite simple. We add some long-range edges. So here we're considering a diamond of long-range edges connecting 2 physical qubits and 2 of these X and Z checks, 1 each. So this is done for not just this particular group, but for all such groups tessellated around the torus, following the symmetry of the torus. I'm not going to draw all of them. That would produce a very eye-watering figure. Here are just a couple examples translated horizontally around the code, but we're also going to translate them vertically. And this gives us an error correction code where each physical qubit participates in 6 checks, 4 that are immediate neighbors, and then 2 long-range ones. This completely upends the structure of the code. So we're going to have significantly more long-range connections now. Significantly more redundant operators now. And this is going to result in error correction codes within this family to have significantly more logical qubits. Second, we are no longer quite so flexible in choosing our code parameters anymore. We can no longer make the torus arbitrarily sized. We can't choose these long-range connections in an arbitrary way. We performed a numerical search over various code sizes and long-range connection lengths and found several examples of quantum error correction codes in this family that do quite well. However, you can't just pick any and expect something good. So here are some examples of quantum error correction codes in this family that are interesting. Here's some notation that appears very commonly in the quantum error correction literature. If we want to summarize the properties of code, we can just use 3 parameters. The number of physical qubits. These are the number of qubits that you actually need to build. You want this number to be small. the number of logical qubits, the number of qubits you have to actually manipulate data. We want this number to be large, and also the distance of the code, which is a crude measure of how much protection that you get. So we want that number to be large as well. So here are some examples of small low-density parity check codes in this family. Here I'm comparing them immediately to a surface code architecture that has similar parameters. So I'm going to choose the same number of logical qubits. And since surface codes can only have odd distances, I'm going to be a little bit generous to surface codes and let them have a slightly smaller distance than the LDPC code that I'm comparing it to. And we can already see with these small examples a pretty dramatic improvement with what is possible with LDPC. You have roughly a factor of 4 fewer physical qubits required for this 72 qubit code on the top right. Now, as we make these codes larger, we would expect this improvement to get more stark. And that's because of that property of surface codes that I mentioned earlier. When you invest physical qubits, you're either investing them into logical degrees of freedom or into more protection. So as we consider larger codes, the difference between logical and between LDPC and surface is likely to get larger. So the poster child of this research work has been this particular 144 qubit code. We call it the gross code. Gross is, the word means a dozen dozens, so 144. And it achieves a whopping factor of 10 improvement in terms of the number of physical qubits you need to realize 12 logical qubits at distance 12. So how well does this code perform in terms of protecting our logical qubits from noise? So here's a very important graph that we see in the quantum error correction literature. On the y-axis, we have the amount of protection. We have the error rate of the logical qubits. And on the x-axis, we have the underlying noise of the hardware. Comparing against the surface code puts a very high bar. Surface codes perform extremely well in terms of noise resilience. So here's an example of how a couple of surface codes do. We see that around the physical error rate that's interesting for us at IBM, where the physical error rate is maybe around 10 to the negative 3, we get significant protection to a logical error rate of about 10 to the minus 7. Another property that's interesting to read off of this graph is the break-even point. At what point is it actually worthwhile to do quantum error correction at all? Is the logical error rate actually less than the physical error rate? And that is called the threshold of the code. And that occurs at around 1%. So that's quite high. So let's talk a little bit about how this noise model is defined. So here we're talking about circuit level noise. There's various ways of doing noise benchmarking in the quantum error correction literature. But here we were interested in the one that's probably the most interesting for a superconducting realization, and that's circuit level noise. You're actually simulating the quantum circuit that extracts the syndrome data, that measures each of the stabilizers. And in that simulation, errors could creep in and potentially mess up your measurement results, potentially have errors lie around in the final state. So that's the circuit level noise model. And in order to perform this kind of benchmark, you need a syndrome extraction circuit. So for the purposes of bivariate bicycle codes, we designed a syndrome circuit that exploits the particular structure of all of the error correction codes in this family, and actually has a constant depth. It's depth 7 no matter how large of a bivariate bicycle code that you choose. So this syndrome circuit does quite well in terms of not letting errors propagate too far. And this can be seen by the performance of the gross code in comparison to these surface codes right here. In the regime of high physical error rate, maybe around 10 to the negative 2, the gross code punches a little bit above its own weight. We have, even though it's just a distance 12 code, it seems to have an amount of logical protection that's comparable to maybe like a distance 15 surface code. And then as you go to lower physical error rates, then you can see a performance that's more reminiscent of a distance 12 code. So having motivated this gross code as something that might be very interesting to build if we can get it to work, let's show how we might realize this code in a bilayer architecture. So I'm going to essentially show how we can take this connectivity graph required by this error correction code and embed it into two planar layers. So to do this, let's first ignore the long-range edges. We'll deal with them later. And we're also going to remove a couple of vertical strips. So I'm going to cut this error correction code vertically and remove a bunch of horizontal edges. So this is what this looks like. If you think about this for a moment, each of these pairs of rings that are connected to one another can simply be layered concentrically, like this. And now you have a planar graph. So this constitutes one layer of this bilayer implementation. So now for the remaining edges, let's look at the edges that we removed. These are these little horizontal pieces, and then let's also add these long-range edges back in. In order to find a planar embedding of these, we are going to exploit the fact that we can rearrange the qubits on the torus. This would also rearrange the qubits in the planar embedding on the top layer, but that's fine. You can always move the vertices around and retain planarity just by making the wires sort of loop around. So if you do that, because of the specific way that these long-range connections are chosen, you can also rearrange the edges in this graph to be a bunch of horizontal strips now. You see the diamond made of those long-range edges is now just a bunch of squares. So these also can be arranged as concentric circles. And this completes the visual proof. Finally, let's talk about logical operations. I mean, after all, what use are your logical qubits if you can't do anything with them? So here, rather than doing logical operations on the code directly, we're going to simply use it as a memory bank and load data in and out for computation on a more sophisticated quantum architecture like that of the surface code. Now, it may be possible to do logical operations on these LDBC memories directly, but for now, let's just try to get this to work. So in order to move data back and forth, we're going to be using a version of a quantum teleportation circuit. So this quantum teleportation circuit takes a little bit of an unusual form because we're going to be implementing it with parity measurements. So first, we're going to initialize the destination qubit in a plus state. We perform a ZZ parity check between the source qubit and the target qubit. And then we do a trick called measurement-based uncomputation to remove the data on the source qubit. This, up to some Pauli corrections, ends up being just quantum teleportation. So how do we realize these parity check measurements? Well, there is a really fantastic tool that was shown in a paper by Lawrence Cohen and co-authors that shows how to implement logical operator measurements on arbitrary quantum error correction codes. The construction is really quite general. And the main idea is to essentially tack on a probe system that connects up to the code and defines a larger quantum error correction code that features the operator that you're trying to measure as part of the stabilizer. So now you start by doing code cycles in the original code, and then when you want to perform the measurement, you perform a code cycle with respect to this larger quantum error correction code, and then you switch back. It's sort of a code switching scheme. It should remind you a little bit of lattice surgery. So this is a trick for implementing these measurements to insert or extract a single logical qubit. But in order to access all of the 12 logical qubits in the gross code, you would need 12 of these systems, times 2, one for X and one for Z. That's clearly quite impractical. So it turns out there's a way of avoiding this, and that is by introducing a family of transversal logical gates. So these are based on an idea of automorphism gates studied by Berkman and Burton. The basic idea is to consider symmetries of the code. Here we have this very nice toroidal symmetry. We can permute our qubits along this torus, and that is a unitary operation that commutes with the stabilizer, so it's a logical gate. And that gives you access to a family of unitary operations that is not particularly useful for computation. But if we conjugate these measurements that are enabled by these systems by these unitary gates, we now have access to a much broader family of measurements that in turn now lets us perform this teleportation circuit on all of the logical qubits stored within the code. So let me conclude. We have shown a quantum error correction code that has a very high encoding rate. It has a factor of 10 fewer logical qubits, physical qubits than the surface code for the same number of logical qubits. It has a fantastic noise performance that rivals that of the surface code, stemming from the design of this fast syndrome circuit that exploits the structure of the error correction code. And it has a high pseudo threshold, a break-even point where error correction becomes useful that also compares well with that of the surface code. Should be physically realizable given only a few more hardware primitives, since it is embeddable in this bilayer architecture. And finally, we've shown how to extract and how to read logical data in and out of this code, therefore allowing it to function as a logical memory bank. I'm incredibly excited about this quantum error correction code. I look forward very much to studying it more in the future and hopefully maybe even trying to build it. And I hope I've convinced you to feel that way as well. Thank you very much for your attention.
Okay. Well, thanks, Patrick, for this very interesting talk. I will have a...
Very nice talk. One basic question, right? In terms of encoding rate, how far is this from the fundamental limit?
From the what limit?
Fundamental limit. So if you think about the best possible code, right?
Oh, that's a good question. So I've seen a couple characterizations of asymptotically best possible limits. But here, when we're talking about these small quantum error correction codes, we're mostly interested in constant factors. I guess if there's a limit on the constant factors of encoding rate that I'm not familiar with, I don't know how to answer your question.
Okay, I'm looking for...
I have a question. So how hard is it to find code parameters? Like you said that there's a lot of freedom in how you choose these cycles.
Right.
How hard is it to find codes when you sweep through the various choices of cycles?
Right.
And have good parameters. Are they typical, or did you have to search?
Right. So this is a fantastic question. The main challenge lies in verifying the distance of a code. So computing the number of logical qubits is relatively easy, but especially for these quite large quantum error correction codes, coming up with exact values or even just bounds on the distance can be quite time consuming. This took a supercomputer simulation. This was not easy.
But is that like typical? If I just randomly choose the cycles, do you get, if you just randomly choose some cycles, did you find that they had distance 12 when you had 144 physical qubits and 12 logical qubits? Or is it like you had to try a bunch of different parameters and run that supercomputer simulation a bunch of times to get something that had the distance that you found?
That's a good question. I did not actually perform the search myself. That was done by one of my collaborators. So I can't give you more detail on that, unfortunately. Now, that said, there are some restrictions on the long-range wires that you require in order to perform this bilayer layout. And you can, certainly when you perform the numerical search, it's key that you integrate those from the get-go.
Yeah.
Hi, nice talk. I saw that in the numerics you extrapolated down to a very low word error rate. Have you thought about the presence of like a noise floor? Because typically we see this when decoding with things like BP.
Yeah, that would be a good question. I mean, the simulations for circuit level noise also get rather expensive. So I think it would be very interesting to further study the properties of this code in those noise regimes as well. Well, for the purposes of this investigation, we were mostly interested in the physical error rates that we encounter in IBM hardware. So that's the regime that we probed to identify the performance in that regime, and as well as trying to find the pseudo threshold.
Great, thanks.
Hi, thank you for the nice talk. I have a question about the threshold and the depth of the syndrome extraction. In the case of color code, if the syndrome extraction circuit becomes longer, this significantly impacts the threshold, right? So your syndrome extraction circuit has a depth 7, but if I understand correctly, surface code is depth 4, since it has 4, stability rate is 4. So it's a bit like almost double the depth, right? So why does this not so significantly impact the threshold? So do you have some explanation on this?
Yeah, I think that's a fantastic question. So I think this relies on the fact that there are several redundant checks present in these LDPC codes. So a lot of the syndrome data that you get from this circuit is actually, redundant, and you can find, you can identify certain syndrome extraction errors that way. So that's one hypothesis why that might be happening. Another hypothesis, I guess, is that the the error properties in these surface codes have this topological interpretation, which is really not present at all anymore in these LDPC codes. The error structure of errors in LDPC codes is not particularly well understood, to my knowledge. So I think that would be really interesting to investigate further.
Great, thank you.
Hi. So currently, you said that you have the capability to do logical load and stores. I'm wondering what your outlook is for its potential capability to handle broader, more general logical operations.
Right, yeah, I think that's a really key question because it's quite expensive to load data back and forth all the time. So the idea that I had in mind was to think through something akin to lattice surgery. So lattice surgery implements Clifford gates through heavyweight poly measurements. So you're measuring multi-qubit poly measurements on many of your logical qubits. As I described in one of the final slides, by measuring a logical qubit via this ancilla system, and then conjugating that measurement with one of these automorphism logical gates, you have access to quite a broad family of logical Pauli measurements. And given access to that family, one could imagine implementing something akin to lattice surgery and realize some family of logical gates. I think this is really fascinating because I don't know how to write a compiler for such an architecture at all. Given a Clifford gate, how does one decompose it into a restricted family of measurements? I think that's a really fun puzzle.
Okay, so more questions?
Thank you very much. I didn't quite understand the embedding into the bilayer, because it looked like the qubits are permuted and then the vertical connections somehow don't match up. Maybe you can comment on that.
Right, so I mean, I guess this is a limitation of the diagramming in this talk. The idea is that qubits can be connected to from both the top layer and the bottom layer. When qubits are repositioned in between the two layers, then it's always possible to retain planarity of either of the graphs. Because when you are given that a graph is planar, you can actually position the vertices of a graph arbitrarily. I thought this point was a little bit non-trivial. Is that the part that you were confused about? Or
yes.
Is it, I see. Well, right. I mean, you could imagine taking a planar graph that with a fixed positioning of the vertices that has none of the edges cross, and then taking any particular vertex and then moving it along some continuous path. And whenever you're about to cross an edge, you simply deform that edge to follow around. This ends up creating a bunch of really long wires, but we assume that we have that capability to implement graphs with long-range connections.
Okay, thank you.
So maybe one last question. So anybody?
Thank you for the nice talk. You seem to mention that you still rely on lattice surgery for the implementation of Clifford gates. Is there some work regarding non-Clifford gates, especially given the connectivity of the model?
Right, so I mean, in the slides, I only gave a method for loading data in and out. You would perform all the interesting logical operations in the surface code computer coprocessor. I mean, perhaps it is possible to realize interesting logical gates on the code directly, But since all you have access to is multi-qubit Pauli measurements, you're going to be restricted to the Clifford group. I'm pretty sure there aren't any logical T-gates, transversal logical T-gates possible on this code. I think you're going to be restricted to the Clifford group, so you're going to be performing some kind of magic state distillation or a code switching process somewhere else in the circuit to have access to non-Clifford gates.
Okay, thank you.
I guess we have somebody there, right? Yeah.
Yeah, thank you for the talk. So if my question is if you put your two layers on a fixed lattice, right? You have a fixed lattice on top layer, bottom layer. Are the connections limited in distance when you scale up your code? Like, do the distance of the connections scale up or get longer as you scale up your code to larger and larger?
Right, I think that's a fantastic question. So, I mean, in the talk, I did not give a particular way of positioning the qubits. I just proved that the graph could be decomposed into two planar graphs. The question of how to best position these qubits in order to make as few of the wires as long or to minimize the length of the wires in some physically relevant way, that work really remains to be done. One obvious thing you could do, at least to realize a torus, is to consider a nearest neighbor lattice for the majority of the torus and then have a bunch of long-range connections to sort of connect the bottom edge with the top edge of the torus, for example. And in that situation, clearly, as you make the torus larger, you're also going to increase the length of the wires.
Thank you.
Okay, so last question. Yeah.
Have you looked at non-error corrected, like injection of arbitrary states into these codes?
So in our nose simulations, we were mostly interested in how well are the logical qubits protected from errors that occur during the syndrome circuit. So that did not involve preparing a particular initial state. However, these are CSS codes. CSS codes have a couple of very nice properties in terms of initializing them to, so for example, an all zero state, if that's what you're interested in.
I was more thinking about like running a magic state distillation protocol on one of these codes by injecting magic state, poor quality magic states, and then doing internal parity measurements.
Right. So I mean, you could think of of using this error correction code as a magic state distillation scheme, right? As you know, when you're performing magic state distillation, you can always frame it as preparing a bunch of poor quality magic states and then projecting into some error correction code. No, we have not tried that. That sounds like an interesting idea.
Okay, so let's thank our speaker again.